Hello and welcome back to part 5 of my operating system development tutorial. What we'll be talking about in this video is very similar to the setting up long mode page on the OSDev wiki. I'd highly recommend reading along as you watch this video. I'll link to it in the description. So the first thing we'll be doing is detecting whether CPUID is supported by our processor. So the first thing we'll do is make a new ASM file. We'll call it CPUID.asm. Right, in our extended program.asm we need to be sure to include CPUID.asm, and in CPUID.asm we'll create our new function detect CPUID, return. Now we want to start protected mode and then we want to detect CPUID. Make sure we make that a call. So detecting CPUID is basically you set a bit in the flags register, copy it back, and if the bit stays flipped then CPUID is supported. So let's do that. So we'll push the flags onto the stack, and then we'll pop that value into our EAX register. Then we'll move the EAX register into ECX, just so that we can compare the two values later on. Then we'll flip the bit in the register, and then we'll push it onto the stack and put it back into the flags register. Now we need to see if it stayed flipped, so we need to push the flags onto the stack and pop it back into our EAX register. And before we get on to comparing those two values, we need to restore the flags to the old version that we stored in ECX. So we'll just push ECX to the stack and then we'll pop the flags. Right, now we can compare it now, so we'll XOR EAX to ECX, and we'll jump if it's equal to 0 to no CPUID. And we'll make no CPUID down here, and we'll halt the application because no CPUID support. Now we need to use CPUID to see if the processor supports long mode. CPUID shows us lots of information about the processor, and I'll link to a page describing that in the description. We are only interested in one value at the moment, and that is the long mode support. We need to create a new function, detect long mode, return. Alright, so we want to move this very large value 0x80000001. That's the value we need to test CPUID against. So we'll test EDX129 after calling CPUID, and we'll just be able to see if the bit is flipped for the long mode support, and if it is 0 then it's not flipped and there's no long mode. So we'll create a new function, no long mode. Halt the application, no long mode support. So jump if equal to 0 to no long mode. I hope that made sense. I was rambling a little bit, but I tried my best to explain that. So we need a comma here. I always forget those commas. Now after the call to detect CPUID, we need to detect long mode, which we'll just call this function here. Now we need to actually enter long mode, but before we get into that we need to enable paging. Paging is mandatory for long mode, so I'm going to show you how to set that up. I'm going to show you how to set up something called identity paging. This means all of the physical memory is mapped identically to the virtual memory. Now if you don't understand what that means, in the description I've linked a page that you can read that should explain paging very nicely. In 64-bit mode we have 4 tables that we need to set up to use paging. We have the page map level 4 table, the page directory pointer table, the page directory table, and the page table. Each of these tables have entries that point to one another, and that's what allows the memory management unit to see which addresses are mapped to which virtual address. To set up these 4 tables, we're going to need 4096 bytes. We've got way more than that at the start of our application right before the kernel, so we'll use that space in there. So first off, we need to create a new file. Let's call it simplepaging.asm. And we'll make a function set up identity paging and return. Then in extended program we'll include simplepaging.asm, and we will call set up identity paging. Right, so the first thing we need to do is define a macro which shows us the entry point of the tables. We'll call this page table entry, and we'll make this equal to 0000. We'll put this right at the beginning of our memory. Then we need to move that into the destination index, page table entry, and then we move the destination index into the control register 3. That just tells our memory management unit that our page table is going to start at that memory address. We're only going to make one entry for the first 3 tables, and for the last table we're going to make 512 entries. And this will effectively map 2 megabytes of memory in our page table. That'll be sufficient for now until we set up a more advanced paging system. Right, so to make our first entry, we need to move dword into the value of the EDI pointer. We'll set 1003. What this does is points to the address of our second table and also sets a few flag bits that we need for this to work. Then we add onto the destination index 1000. Then we move a dword into there, pointing to the next table, and so on and so forth. Now that we're at our last table, we're going to need to map 512 entries. So to do that, we'll move into the EBX register 00000003, and that's just the flag bits that we need. Then we'll move into the ECX register 512, and that'll let the loop function know that we want to loop 512 times, effectively adding 512 entries. Then we define a sub function set entry, move dword into the value at the EDI pointer, moving in EBX, adding to EBX 1000, adding to EDI 8, and then looping back to set entry. Now we need to activate the physical address extension paging by setting the PAE bit in the 4th control register. So move into EAX control register 4 or EAX 1 on the bit, the 5th bit, and then move it back into the control register 4. Now the last thing we need to do is set the long mode bit in the EFER model specific register. Now that's just like this, and what we're basically doing is just setting to the address of the register that we're trying to change, reading from that register, setting the bit, and then writing back to it. And now to enable paging, we move EAX CR0, moving the control register 0 into EAX, setting a bit in that, and then moving it back. Right, so we have paging set up. The last thing we need to do is edit our GDT to be a 64-bit GDT instead of a 32-bit GDT. There's a few things that we're going to need to change, but for the most part it's going to be basically the same thing. So into our GDT file, we can create a function called edit GDT. We need to put bits 32 because we'll be calling that from 32-bit space, and we need to do bits 16 after it so that we don't mess up our older code. So we return from edit GDT. Now we need to change this value, and we need to set this to a quad. So this was a double word before, now it's a quad because we need to access a 64-bit address space. And these, we just need to set them as specific bytes. So move GDT code disk plus 6. To edit this value here, we get this address plus 6. And we need to move in 10101111B for a byte value. And we do the same with the data description as well. There we go, we've successfully made a function to edit our GDT to a 64-bit GDT, setting these as bytes so that the assembler knows how big of a value we're moving into there. Now we call edit GDT. Right, now our processor will be in 64-bit mode. We need to jump to a 64-bit function. So start 64-bit, and we will jump infinite. Now we need to tell our assembler that this is going to be 64-bit code, so we do bits 64, and we need to do a far jump. So just like we did up here, jumping into 32-bit, we need to do the same jumping into 64-bit. So code seg start 64-bit. And one last thing I just realized we had to do is we need to move these from up here to down here. Since these were up here, they were being compiled in 16-bit mode. We could have surrounded it in bits 32 and bits 16, but I think it's just easier to include it down here. That's just my personal preference. Right, now let's actually do something in 64-bit mode to prove that we're in here. Normally we would have to update the segment registers like we did when we moved into 32-bit mode, but since we're using the same GDT and the same data segment, if we did this, it would be just doing the exact same thing, so we don't really need to do that. Right, now let's get on to actually doing something. So we move into the destination register, our video memory address, and then we move into the RAX register, which has now become available because we're in 64-bit mode, this hexadecimal value. 1F20, 1F20, 1F20. And what this is just 20 is a space and 1F is a color code. So we'll have a space that has a foreground color of 1, which is white, and F, which is blue. Then we move into the ECX register 500, and then we repeat store chord. So that'll copy this into this many times, and each time incrementing this. Right, now let's run that and see what it does. As you can see, we've got a fully blue screen. That's because this function here clears the screen. Well, technically, it sets everything in video memory to this little string here. Right, so now we're successfully in 64-bit mode. I hope you learned a lot from this video. In the next video, we'll be focusing on probably making a GCC cross compiler so that we can write some C code and make something more useful. As always, thanks for watching, and I'll see you next time.